Okay, so solving absolute value equations, we can see that the SC, what we're trying to do is very direct, solve absolute value linear equations. That's from this first page of this section. And we are going to solve this first using a graphing method, okay? So in order to solve the equation 2 times the absolute value of x minus 5 minus 4 equals 2, what we can do is we can graph f of x equals 2 times the absolute value of x minus 5 minus 4 on a graph. So basically what we're going to do is we're going to take the left side of the equation and we are going to graph it. Okay, rather than doing it on the graph that they provide, I am going to use the calculator. Okay, and so I'm just going to add a graphing page and type in here the 2 times the absolute value of x minus 5 minus 4. Notice I'm only putting the left side of the equal sign into the calculator. It's x minus 5 minus 4, is that correct? Is this correct? For that example problem, okay? And so there is the graph of that, all right? What I then want to do is I also want to graph on here the other side of the equal sign, the 2. I want to graph a second function that's just y equals 2. Okay, so I'll go to the calculator and type in just the y equals 2. That's going to be a horizontal line that goes through the y-axis at 2. As a matter of fact, every point on that red line has a y-coordinate of 2. Once I have both sides of the equation graphed, in order to find the solution, what I want to find is where do the two functions intersect. So I can see they intersect once right here and again right here. Those two, the x coordinate of those two intersections are the solutions to this equation. They are both values that will make the equation true. Now we can kind of eyeball it and see that this x value is going to be -2 and this x value is going to be a 9. But I also could go to menu, go to analyze graph, and you would see that in that submenu is the option for intersection. And then just move the vertical line to the left, hit enter, move it over to the right, hit enter, and I can see that the intersection here is at 2, 2. Okay. And same thing for the other intersection. Go to menu, 6, 4, and find out that that intersection is actually 8. I called it 9 a minute ago, and it is actually 8. Okay. So then we would be able to conclude based on that, that the solution here is 2 and 8, not 2 comma 8, but 2 and 8. Those are not, it's not a point. Okay. So fill that in here, x equal to 2 and x equal to 8. Okay. Now then, again, the thing about this is that this method for solving an equation will work no matter what it is, whether it's an absolute value or a quadratic or a cubic or whatever kind of function it is. You can use this method to solve it. Okay, so a good question is asked here below this on the reflect number 1. Would you expect, now this one had 2 solutions. Would you expect most absolute value equations to have 2 solutions like this? And you could argue that no, but I think they're probably wanting the yes out of this. You actually could make a good argument for no. But they're looking, I think, here for an answer of yes, and that's because if you think about it, what we have is we have one side of the equation is going to be a v, And the other side of the equation is and the other side of the equation is a number. So that V is going to end up being a horizontal line. So that horizontal line is going to intersect that V usually twice. Okay. Is it possible that an absolute value can only have one solution or no solution? Okay, I just lost contact there with the computer. Okay, and could you figure out a way based on what we said here about how a solution to a absolute value equation works graphically? Could you figure out a way in which you could have an absolute value that only has one solution? That means that they only intersect one time. They only cross each other one time, right? Well, certainly I could figure out a way to make that happen. So I'm trying to develop a absolute value equation that would only have one solution. So this would be one example of such a type of absolute value equation. That would have only one solution because the horizontal line would only touch the V once. So there's one solution. Remember, the solution to an absolute value equation like this is going to be where they intersect. Now then, if I was to move that vertical line down, now we have a situation where we have two solutions to the absolute value equation if we were to have equations written from these graphs. Okay? If I was to slide it up, now how many solutions would this equation have if we wrote an equation from this graph? How many times does the line intersect the V? None. So there would be no solutions in this problem. Could you devise a way that you could end up with three solutions? Well, no, there's no way that this line is going to intersect this V no matter how I set it up more than twice. So it's possible to have no solution, one solutions, or two solutions, but there is no other possibilities than one of those three. Okay? So let's look at the next page, page 80. Okay. So let's read that first sentence right here. To solve an absolute value equation algebraically, which is what we want to do this algebraically, we want to first isolate the absolute value expression on one side of the equation the same way you would isolate a variable. So we want to isolate the absolute value expression part first. Okay. So in this problem that they give us, this example problem, we want to isolate the absolute value of 3x first. So that means that we want to get this part by itself. Well, how do you do that? Well, you subtract 2 from both sides. Now that isolates the absolute value part. Okay. Now then, this is where you have to have an understanding of an absolute value. An absolute value is how far a number is from 0. Okay. So we're trying to find out what's going to make this equal to a 6, where there's two numbers that are going to have an absolute value of 6. Those two numbers are 6 and -6. Okay. So therefore, once we after we isolate the variable, we then want to write two equations. Okay.